ensure that this switch is on. Then you have to ensure this switch is on. Then you have to ensure this switch is on. So all these are very important to ensure that we are getting an interrupt. Okay. There are three major registers: interrupt flag register, interrupt enable register, and interrupt the global interrupt register. Okay. The global interrupt register is INTM. Okay. If that is on, then only you can start all the interrupts. Now we'll see from the yesterday's code how and why initialize system control. Okay. If you want to see what is there in initialize system control, you can just press control and just click this. Okay. You will have the initialize system control. It is just for initialization purpose. To be in a simple words, initialize system control is required for initialization purpose. Don't worry more about it. Okay. Then there is one line here. Control register. There is peripheral input control register. It is again required most of the cases. If you look here, initially you will have to clear the flags. So interrupt enable register and interrupt flag registers are all made 0. Okay. Maybe something is there, you should make it initially 0. This interrupt 5 vector table, the details can be seen here. Again, I would say we need not go about it. Interrupt 5 vector table basically stores the address of the interrupt service routine where you are writing that function. Okay. We need not again worry about it. Thing that you need to focus here is this line. So for example, if you see here in this code, you are only using CPU timer interrupt service routine, and that address is stored in there's a register called Ti timer interrupt 0. And that you can find the register details in the data sheet. For example, if you go down, Pi control register. Okay. If you want to see the data of that, you can see what all is there here. For example, if it is 0, then it does something. If it is 1, there is something. Okay, there is another very important interrupt called interrupt acknowledge register. This is very important in interrupt service routine. You need to always acknowledge the interrupt if you want to receive the interrupt again. Okay, so we always need to put that acknowledge interrupt. We are using only one interrupt here, CPU timer. So that address should go to Ti and T0. Okay, it's already written. You need not. Then this is the configuring CPU timer. So again, we are using 150 MHz clock, and this is the time in microseconds. Okay.
That 150 is changeable?
No, yeah, that through internal PLL we can change. We can change, but 150 is the maximum, so it's better to leave it there. PLLs are coming a bit later. Yeah. Now let's see here. Now this is a line. We need to understand what is this line. So IER, I hope you know that symbol, dash. Dash is OR. IER is equal to IER ORing with a number, a name called MINT1. MINT1 is not syntax, it is a variable. It's actually a macros. I don't know whether you know it.
Define.
If you want to know that what is the value of this, just press control and click this. If you press control, you will get this symbol. If you remove the control, it will go. So press control and click that. You know that it has got a value 1. Okay. Now we need to understand what is this. Now you have to see this register. INTN1 means it is interrupt group 1. Okay. Now in interrupt, why we are interested in interrupt group 1? Why not in group 2, group 3, group 4? That is because if you look into the data sheet, timer 0 interrupt. Timer 0 interrupt is in interrupt group 1. Okay. Can you see where is timer? The timer 1 is in interrupt 13. It is not in interrupt 12, and timer 2 is in interrupt 14. It is not there here, but it is there. Okay. So in interrupt group 1, timer 0 is there. That is why to tell the controller we have to write this line. And here I am trying to. There is a register called interrupt pi. This is a register. So each we have to see that in group 1. Let me see what is this PIE IER1. So that one you have to go here. So we know that timer 0 is in group 1 and which bit? There are 8 bits. 1.1, 1.2, 1.3, 1.4, 1.5, 1.6, 1.7. That bit has to be made high. Okay. That is why if you go to the code, you will see that interrupt X bit high. This is basically telling that to enable this bit 1.7. This is also very important. If you don't write this code, then the interrupt will not be serviced. It's like closing the switch. You have to close that switch. So that is the procedure. And then coming to the infinite for loop. And if you see in the for loop, we need to acknowledge the interrupt. This is very important. This is to acknowledge is important. This is to receive more interrupt from the loops. Actually, we also need to clear the flag. We do that for EPWM interrupts. Here we need not. I do not know why it's not done, but it works. If you go to EPWM interrupt, we'll see that then they clear the flag. Here anyway it's not required, so this is what is here. In 28335 there are 88 GPIOs. Okay, divided into 3 groups: port A, port B, port C. Port A handles GPIO 0 to pin number 31. Port B handles pin number 32 to pin number 63. Port C handles pin number 64 to pin number 87. Okay. So there are 3 ports. And each of these GPIO is multiplexed with 4 functions. Either you can use it as GPIO, or you can use it as peripheral 1, or you can use it as peripheral 2, or you can use it as peripheral 3. Okay. So each GPIO can operate as a GPIO, or it can operate as peripheral 1, peripheral 2, peripheral 3. It is like merging.